Alright, so let's begin lecture 21, which is on orthogonal coordinates, integration and orientation, and total curvature. So this is kind of a seemingly disconnected bunch of stuff, but you'll see it connects in the end here. Of course, all of these things, well, these two things, integration, orientation, and total curvature, are certainly needed to understand the Gauss-Bonnet theorem, which is one of the more interesting results we'll see in this course. So this is a necessary discussion. I'm going to use my notes from last time I taught this course from Chapter 6, Part B actually. Sorry for the break in format, but I think they're pretty good already, so there's no point in reinventing the wheel here. Now I'm going to have to do some zooming in and out, so my apologies in advance if this goes wrong. Let's see here. All right. So, make myself a little mark here to try to not talk about stuff off the screen. So the central equations of last section were the structure equations, right, which essentially define the connection form. And then, of course, the exterior derivative of the connection form being given by the Gaussian curvature. Now we're going to develop some nice formulas for how to calculate things in a particular context. As you may recall from our previous work, the orthogonal coordinate patch is really nice. So orthogonal coordinate patch has the partial velocities being orthogonal, and the corresponding frame field, of course, you can just get from normalizing the partial velocities. Basically that means you end up dividing by the square root of e and the square root of g. Alright, so we're now going to use some notation that we've used in the past, which was, it's really chart notation, and it's just because we don't want to write a bunch of tildes everywhere, but we'll get to it soon. I'll just, just some notation here. So, if you think about it, u is a function from xd to d, v is a function from xd to d. Well, that's a viewpoint we can take, right? Now you think, well, u and v were just, they were, variables in R2. Now you're saying that they're functions from R3 to R2. Right, exactly. So in other words, I'm saying u and v are component functions of a chart. It's a mapping from R3 back to R2. All right. Now technically we used u tilde v tilde for these before, but in any event, we have E1 is that, E2 is this, and dual forms, right, theta 1, theta 2, sorry, my 1 and 2 are down now, because I'm being lazy, sorry. So of course it's dual, and we have these four relations, du xu is 1, du xv is 0, the push forward by v of xu is 0, the push forward of v by xv is 1. We actually worked these out in the previous lecture. It's also exercise 7 of section 4.4, but there were u tildes and v tildes scattered about. Okay, so the claim then is that theta 1 you can get from the square root of e times du, and theta 2 is the square root of g times dv. Now, this is where I really should probably have du tilde and dv tilde, because these are forms on the surface, and you might complain, well, du and dv are forms on the parameter space down in R2, but that's, well, that's the abuse. So, anyway, I'm just following O'Neill, so it's all his fault. All right. Yes. So there you have it. Basically this division by square root of e and square root of g and multiplication by square root of e and square root of g, they cancel out, right? And then on the other hand, the forms are dual, so the vu and the uv are both 0. So there you have it. This is a way to calculate the coframe for an orthogonal patch. Very simple. So to calculate exterior derivatives, and I want to do that because I want to look for a formula for omega 1, 2, which remember is based on the derivative of the connection form. So if I was to exterior differentiate theta 1, that would mean I have the exterior derivative of this, which by the product rule gives me exterior derivative of square root e wedge du, square root of e, and d wedge d of du, but of course d squared is 0, so that piece is kaput. And this piece I have to partial u and partial v, alright, du dv. And I suppose that there's like a little lemma I'm using right there that maybe we haven't proved, but you can prove that in fact this is equal to that. Any event, we'll have plenty of time for those sorts of abstract calculus comments when we study manifold theory proper. So just take it on faith here if you don't mind. And then, so of course this is the derivative of the square root of, sorry, I'm missing something here. What did I do? Oh, I changed this, I want a theta 2 instead of a, why am I doing this? Because remember that, I mean, you gotta remember what we're looking. Remember, d theta 1 is what? It's omega, oh goodness gracious. Oh, come on. I want to make sure I don't have a sign error here. I will find it. Bear with me. So d theta 1 is omega 1, 2 wedge theta 2, right? So the reason I'm rewriting it that way is so that I can see what omega 1, 2 should be. Now theta 2, remember, is what? Well, you remember theta 2, as we were just mentioning in our previous claim, theta 2 was the square root of g dv, right? So to get that square root of g there, and what I'm doing right now, you just, what do? Well, divide and multiply by square root of g. So multiply by square root of g on this, and divide by square root of g there, so I can pull the dv over here. And let's see here, something else. Oh, of course du wedge du is 0, so that piece vanishes, duh. So we're just left with this piece, and then we divide and multiply by square root of g, and that gets us to here. And the minus is because I had to change the order. Du wedge dv is minus dv wedge du. Likewise, d theta 2, by a very similar calculation, is minus square root of g, the u partial derivative divided by e dv wedge theta 1. You know, however, the first structural equations state this. I mean, this would be a really weird calculation if you weren't thinking about this, right? It's like, why would I simplify this to that? That's weird, but okay. Anyway, so that said, of course, all right, we've done this before. This is just rehashing things we know. Sorry, let me make sure I'm still in frame. Ow. Talk to my cameraman for a second here. Yeah, okay. So we just figured out that this and that were, well, this and that I can calculate from the formulas in the previous page to be this and that respective. So there, anyway, there you have it. Omega 1, 2 is this lovely thing right here. All in terms of the E and G functions for the patch we're looking at, right? Now, as an application, we can calculate the 1, 2 form for the sphere. Now, I think I'm just, this is last time I taught the course, so I was following O'Neill a little bit even more closely, and I have not, this formula may not be consistent with the parameterization I've used for the sphere in my notes, okay? Anyway, you have E, F, and G like this, and so that gives us theta 1 r cosine v du and theta 2 r dv, and so here's your partial derivatives of E and square root of E and square root of G respective, And so there you have it. The 1-2 connection form is just sine v du, just like that. So, Gaussian curvature from intrinsic calculus then. Let's get to it. So we can derive, we have everything we need then to find a formula for the Gaussian curvature k in terms of the E and the G. There's no f is equal to 0 here because we're working with a principal patch, not principal, excuse me, orthogonal patch. May or may not be that this is principal, I don't know. D omega 1, 2, of course, is minus k theta 1, which theta 2, right? But now I have this lovely formula for omega 1, 2. And of course you can calculate theta 1, which theta 2 is just the square root of EG du wedge dv. That's easy enough to do, right? So then we just have to exterior differentiate the 1, 2 form. Just move that up here. So the exterior derivative of the 1, 2 form is partial derivative of this thing with respect to v dv wedge du. Oops, sorry, I put an off frame. And then the exterior derivative of the v component with respect to u du wedge dv. Now, there's a minus that I get from flipping that over that cancels this minus, and it just leaves you with du wedge dv in a sum of two terms. But then to change the u and dv to theta 1 and theta 2, of course I can do that trick again, multiply and divide by the square root of the e and g functions, and there you have it. This animal right here has to be minus the Gaussian curvature. And so that brings us to, we have proved the following proposition. If x is an orthogonal patch with e and g as defined as usual, the Gaussian curvature k is simply given, sorry, my pages are showing. The Gaussian curvature is simply given by minus 1 over the square root of eg times the, okay, so you differentiate the square root of the g function with respect to u, divide by the square root of the e function, and then partial differentiate all that with respect to u. It's kind of a second derivative kind of thing in here, right? Likewise, you differentiate the square root of the e function with respect to v, divide by the square root of g, and then all of that you partial differentiate with respect to v. So these kind of slightly complicated second partial derivative expressions, and there you have it. That's the Gaussian curvature. Now, because you might remember we have that an isometry preserves e, f, and g, right? E is equal to e bar, f is equal to f bar, g is equal to g bar. That was a convenient criteria to decide whether or not f was in fact an isometry. So given all that, you can see then that the Gaussian curvature is it's going to stay the same when you go from m to m bar, because the formula is just written in terms of things which are preserved under an isometry. So there you go. There's another proof of Gauss's awesome theorem. And I think, I could be wrong, but I think historically it was probably proved more like this to start with. I mean, differential forms, although they haven't been played with since the time of Pfaff, they really only came into their own more recently. Okay, especially since Cartan. All right, so anyway, that's a lovely formula for Gaussian curvature in terms of E and V. That brings us to section 6.7, which is on integration and orientation. Make sure I'm in frame still here. All right, let's find my cover page. Where was it? All right, so first of all, we should just talk a little bit about two segments, and two segment being patch-like. What's that mean? So you have a rectangle, say from A to B for U and from C to D for V, and so there's an open set, right? Then a two segment, that's the interior of this closed rectangle, right? A two segment from R to M is patch-like, provided that if you drop the edges, it's a patch. In other words, it's at least injective on the interior and regular. So that means that the partial velocities are linearly independent. The cross product, in other words, is non-zero of the partial velocities is another way you could characterize that. Two dimensions are so easy. All right, anyway, so to calculate the area, what we could do is we can integrate the square root of EG minus F squared over M. So I'm not motivating this. Sorry about that. You can look at my calculus 3 notes. I think I motivate these sorts of things there, I believe. Anyways, the area you can get from integrating the square root of EG minus F squared over du dv. So of course this could be improper if D is open, so you could then integrate over two segments and add them together as needed. All right, anyway, so here's an example just to show you that while I am not motivated, I have not motivated that formula. Here's an example of how it works. So the sphere, in at least O'Neill's notation, E, F, G are this, and this, and this, r squared cosine squared v, r squared. Again, following O'Neill's formulas from page 296. So you calculate the W. I think this actually, was this W or square root of W? I cannot remember. Maybe it's W. In any event, out pops r squared cosine v, because when we use v going from minus pi over 2 to pi over 2, cosine is non-negative there. And so the area ends up being the integral of r squared cosine v dv du over this minus pi over 2 to pi over 2 and 0 to 2 pi. Of course, this is constant in u, so we just integrate the du to 2 pi, and cosine v integrates to sine v, evaluated from minus pi over 2 pi over 2 by fundamental theorem of calculus, part dos. And so that gives us 2. So 2 times 2 is 4. 4 pi r squared. Aha! The surface area of a sphere is 4 pi r squared. I hope that takes you to your happy place. I know it takes me to my happy place. So anyway, there we go. So our next thing we're going to need to talk about is a paving. A paving of a region, P, is in a surface M, consists of finitely many patch-like two segments, right? x1, x2, xk, whose images fill P such that the union over the images of these patch-like two segments, every point in P is in a particular patch-like two segment. So they're not, sometimes if you look at something like this, there could be some overlapping. These just join up on the edges, all right? So they're not overlapping. We don't double count areas. It's just kind of like non-overlapping scales or something. By the way, an entire compact surface is always pavable because, that seems like a misspelling. Oh well, anyway, it's always pavable because, of course, every open cover admits a finite subcover, and so in that finite subcover you can build these things. All right. That said, we should talk a little bit about orientability. An area form on a surface M is a differentiable two form, all right? Where for any pair of v and w in the tangent space, we have mu of vw is plus or minus this lovely formula, which you should recognize from Lagrange's identity as plus or minus the magnitude of the cross product of v and w. This plus and minus is not avoidable, right? Remember, there's two orientations locally for M. On the other hand, if we use an orthonormal frame, then this area form works out to plus or minus 1, right? So that's good. Move along here. Not really getting too deep into the theory of integration for surfaces, and I'm sorry if that's something you're interested in. I'm not really going that direction, so you can hopefully forgive me about that. I really should teach a serious course in integration sometime. Oh well, hasn't happened yet. A surface M has an area form if and only if it is orientable. On a connected surface, there are exactly two area forms. We denote these by plus or minus dm. All right. So this is really, in the nuts and bolts of things we've done before. But, what was our definition of orientable? All right, well, I guess it depends on which page you looked at, but certainly one definition you could give for orientable is that there's a non-vanishing two form on the surface, right? But if you go back and look at chapter 4, like page 186, 187, you can see that M is orientable if and only if there is a unit normal vector field on M. I think I went through that in a previous lecture. And there's also this fundamental identity from there, which is that the mu of VW is u dot unit normal dot V cross W, right? So in this way, the unit normal induces a two form on the surface. So we can go back and forth between unit normals and two forms on the surface. So here's a definition, then, in view of that lovely bit of technology. If X is patch-like two segment in a surface, oriented by dm, all right, then the integral of dm over the patch-like 2 segment, right, is the corresponding double integral, right, of dm evaluated on xu comma xv, the partial velocities, du dv, right? Now, this could either be positive or negative, all right? It's going to be positive if x is positively oriented, and if it's positively oriented, this integral actually represents the area. You could work it out. It would work out to that square root of eg minus f squared we saw before. On the other hand, if this quantity is negative, that that it's going to give you minus the area, all right? So if you have a positively oriented paving, in other words, if you have a finite number of patch-like 2 segments, each of which is positively oriented, and you sum over all the patches, then the sum of the integrals over the patches gives you the total area of the P, the area, the region P, which is pavable. All right, so usual integration stuff to get total area, break it up into pieces, find the area of each piece, add them together, voila, got the total area. Bam. So this leads us to the definition of the integral of a 2 form over a pavable oriented region, P, subset of the surface. What we do is we simply, take the sum of the integrals over each patch-like 2 segment and add them together, all right? Now, you'd say, well, but how do we integrate a 2 form? Well, to integrate, I mean, I just showed you how to integrate the orientation form for the surface, right? The dm, but any other 2 form has to be just a scalar multiple times dm. So this actually it's natural extension of the definition we just looked at here for this one. If I can integrate this, I can integrate f times that in a natural way. Here's how. So definition. Well, here's why it's interesting, actually. If K is a Gaussian curvature of a compact surface M oriented by area form dm, then the integral of K dm is called the total Gaussian curvature of M. So how do we calculate it? The total Gaussian curvature of any pavable region P is calculated in the same way. What you got to do, you find a paving of the surface, and then you find the total curvature for each 2 segment, and add them together, and that gives you the total Gaussian curvature of a patch-like 2 segment, of a pavable region, rather. So here is the details of that in terms of the E, F, and G stuff. Integral of K dm would be the integral over the pullback, actually. So if you look at the formula we had, that's actually the formula for the pullback. I mean, if you understand this, great. If you don't, here's the formula. So K of x, the square root of Eg minus f squared du dv. So basically we just take that area integral and you multiply by the function that is in front of the area form. Well, it could be plus or minus the area form again, depending on the orientation of the patch. But all right, so anyway, some examples are probably good to look at. Make sure I'm in frame again. Consult my cameraman. There we go. All right. So some of these we've done, some of these we haven't. But for constant curvature, for example, if the curvature is constant, then the integral of K dm is K times the integral dm, right? So actually, for constant curvature, we just take the Gaussian curvature and multiply by the area. That gives us the total Gaussian curvature, right? So for example, the total Gaussian curvature for a sphere is 1 over r squared times 4 pi r squared. Hey, we just calculated that. Haha. So the total Gaussian curvature for a sphere is 4 pi. We didn't calculate this, but there's that bugle surface, which is also the pseudosphere, although apparently that term has come and gone. Anyway, I didn't get this into the lectures that I've taped, but the bugle surface, you can calculate the area of that is 2 pi c squared, and the Gaussian curvature of that was also minus 1 over c squared, so the total Gaussian curvature is minus 2 pi for the bugle surface. Torus. What about a torus? Well, a torus has, you know, the pullback of dt is r parentheses r big R plus little r cosine u du dv. That's the for the patch on the torus, which remember the torus is covered by that one patch, right? So the Gaussian curvature we also calculated for the torus to be this, right? Cosine u over r plus, well, that was this lovely formula. We talked some about it the other day. And so if we integrate k dt, remember dt was this, but you see what happens? Let me just draw your attention. So we got this right here in the area form for the torus. The Gaussian curvature also has this factor. So they cancel. Woo! And they just leave you an integral of cosine u over the full parameter range, which integrates to 0. So apparently the total Gaussian curvature of the torus is 0. But if you were to imagine, say, just taking the inner part of the torus, or let's see if I can foolishly try to draw it. So here's, well, not how I usually draw it, but like there's this outer part of the torus, right? So the outer part of the torus is like from what? From u. U is, you know, it's like pi over 2 to pi, or the lower half of it's like you know, minus pi minus pi over 2, you know, and then the inside of the torus, right in here where k is less than 0, in there, that's for like minus pi over 2. I can't draw. Less than u, less than pi over 2, right? And so, of course, the Gaussian curvature is negative in there, if I remember right. Although I'm having trouble seeing it with the current formula. Oh, anyway, we talked about that the other day. Let me shut up about it. So, anyway, you can see if you integrate from minus pi over 2 to pi over 2, you get, you know, you get like 2 pi from this, and you get a 2 from this. So you get 4 pi for the inside. I mean, I think you get minus 4 pi for the inside and 4 pi for the outside, or vice versa. I don't have quite enough details here to be sure about the signs. But the point is, the total curvature of the inside of the torus and the total curvature of the outside of the torus, they're canceling. All right. Anyway, catenoid. So, catenoid. Again, we can calculate the total curvature. I'm not sure we actually derived this. I can't remember if we derived it or not, but the curvature of the catenoid is, it ends up involving a cosh squared. And so you do this integral, and out pops this. But as a goes to infinity, we get that the total Gaussian curvature goes to minus 4 pi. Well, this is interesting. So we have all these different surfaces, and certainly for the ones which are compact, right, like the sphere and the bugle, this bugle surface and this catenoid surface are a little hinky. But certainly for the compact ones, we get 4 pi, we get 0. It must not be an accident, right? All integer multiples of 2 pi here. The total Gaussian curvature, all integer multiples of 2 pi. That is curious, is it not? All right. So that brings us to our last little bit of this lecture. Let M and N be surfaces oriented by the area forms dm and dn. Then the Jacobian of f is the real value function jf on m such that when you pull back the dn, it's jf times dm, right? Now this is a 2 form, that's a 2 form, so it stands to reason that the pullback has to just be some function times that. And he's saying the Jacobian is defined to be whatever function it needs to be in order to get this equality here. So let's see, let's think about that a little bit. So if we calculate the Jacobian of f times dm VW, allegedly that's going to be the pullback of dn acting on VW. But the definition of the pullback is that it's just the form dn in this case acting on a pair of push forward vectors, right? Push forward of v. Oh, goodness gracious. Sadness. This is a very, very naughty typo. That should be down for sure, okay? Push forward, not, this is bad. Oh, sadness, sadness, sadness. If only I had some white out. Oh well, sorry, I do not. I'm gonna get some though, I'm gonna get some. All right, so note, if f is regular, if f regular means that the Jacobian is not equal to 0 because, well, let's see here. Well, this is all proportional to like a cross product of these things or those things. So, oh goodness gracious. Well, I'm having trouble thinking of how to explain that right this second. I mean, f being regular means that the Jacobian matrix, right? Or if you like the differential, the push forward rather, f lower star is invertible, right? So if this were 0, that would mean that this is 0, but that need not be the case because this is also, oh man. Well, I'm going to leave this exercise to the reader for the moment because we're too far into this, too far in this video to bail. Excuse me. F is orientation preserving if the Jacobian of f is positive. F is orientation reversing at P if the Jacobian is negative. Moreover, let's see here. Moreover, what do we have? The Jacobian of f, well, the absolute value of it, is the absolute value of the area form of M on VW with the absolute value of the area form on N on the push forwards of V and W. Oh, look, it's push forwards. I got the star downstairs where it belongs now. Yay! So this is the rate at which f is expanding area at P, essentially, right? And so, just to bring a little bit more clarity to what's going on here, if we integrate the Jacobian of f times dm, that's the same as integrating the pullback of dn over m. And in any event, that's the signed area, right? It ends up being the signed area of f of m, aka the algebraic area. This could be plus or minus depending on the orientation of f. Now, it brings us to the Gauss map. Mostly we're using that determinant, the Jacobian thing for the sake of this Gauss map here. So the Gauss map is a natural mapping you get from the surface to the unit sphere, which is basically you take the unit normal on the surface and then you like just put it over to the sphere, and you just take these unit normals and identify them with points on the unit sphere, as of course you're free to do, since the unit sphere in some, well, not in some sense, it does contain all possible direction vectors, unit direction vectors in R3. There's a silly picture of it. Here's my surface M, here's the Gauss map G, and so you think about taking these arrows and they map over to here to points on the sphere like that. Now, here's the theorem. Here's partly why we're interested in it. The Gaussian curvature K of an oriented surface M is the Jacobian of its Gauss map. So here we go. We've had several different ways to see the Gaussian curvature, right? To start with, we had the product of the principal, curvatures. It was the determinant of the shape operator. More recently, it's become the coefficient of theta 1 wedge theta 2 with the exterior derivative of the 1-2 connection form. Then for the orthogonal patch, we had it in terms of this lovely second partial derivative formula for the E and G, the warping functions, right? It had it in terms of the warping functions. And now, yet another interpretation of the Gaussian curvature. Gaussian curvature K is, in fact, the Jacobian of its Gauss map. Now, I have seen this given as a definition for the Gaussian curvature in other texts, and I can tell you that I much prefer the path that O'Neill has taken, because to me, I mean, I don't know, some people take great geometric comfort in this definition, and I guess to each his own, but anyway, let's make the connection now. So if you have a unit normal with coefficient functions g, g1, g2, g3, right, then remember the shape operator is defined by minus the covariant derivative of v of the unit normal. So if I put the minus over here, I just have this lovely formula. So the vector v acts on the component functions of the unit normal, and then we make it a vector. So there's u1, u2, u3, where those are the standard Cartesian frame in R3. So, great. By proposition, I'm going to put the theorem out of frame. Be okay. By proposition 7.5 on page, unknown page. Anyway, this is the formula for the push forward. It's basically a vector of directional derivatives when you're dealing with a function like this. So anyway, when you do that, so it's basically just looking at, this is the formula for the push forward, which we've worked out before. And so when you do that, the push forward under the Gauss map, right, of V is V of GI, UI of G of P. All right. So, but what does that mean? Well, look at this. So if you look at star, right, and you look at this up here, which by the way, these were also at those points, you can see that these are proportional, right? In other words, minus the shape operator acting on V is parallel to the push forward under the Gauss map of V. And we're trying to show that KDM is the pullback under the Gauss map of d sigma, where d sigma, that's the area form on the sphere. So we're trying to show the pullback of the area form on the sphere by the Gauss map, right, is KDM on the surface. Now let me just draw that back on my little picture over here for a second, just to try to get it in our mind's eye. So you can think about, at least, I mean, you'd say, well, the two form doesn't exist on the sphere either. Well, fine, got me, but it's a helpful picture. So here's the two form on the sphere, and then we pull that back over here. Supposedly it pulls back to KDM, which is a two form which lives on the surface M. All right? Pull back a G. All right? That's the claim. Oh, man. Oh, duh. Sorry, I wasn't done with the page yet. So here's the proof of that assertion. We seek to show that the pullback of the area form d sigma on the sphere is the KDM form on M, K being the Gaussian curvature. So this is, it uses a lot of pretty powerful lemmas and identities that we've derived over the course of this course. A lot going on here. KDM acting on VW, first of all, is K of P times dm VW. That's just definition of scalar multiplication. Then dm, right, is U of P dot VW. That goes back to our discussion about how orientation is interchangeable between unit normals and two forms, non-vanishing two forms. That identity we derived in that discussion. It's just the unit normal dot the cross product of the vectors. But also the unit normal dot the cross product of vectors was the shape operator of V cross the shape operator of W, dotted with U of P. That's lemma 3.4 of chapter 5, I believe, if I trust myself. Sometimes I do. And then on the flip side, if you pull back, oh goodness gracious, oh, what idiot wrote these notes, I swear. Pull back under G of d sigma, good grief, on VW is d sigma, right, acting on the push forward of the pair. That's the definition of pullback on a two form. And of course then this again by that orientation discussion, is the unit normal. This is the unit normal on the sphere, dotted with these guys, and that of course is just u of p dot sv cross sw. But these then are equal. Well, I guess that's not on the sphere. That's on the well, is it on the sphere? I think there may be a geometric thing going on right there. Anyway, the point is that these are equal, and so we have it. The pullback of the area form on the sphere is the area form times the Gaussian curvature on the surface. So a corollary to that then is the total Gaussian curvature of an oriented surface M is equal to the algebraic area of the image of its Gauss map, which is pretty awesome, right? So integral of k dm is the integral of the pullback of G, pullback of the area form over M, but that is equal to, of course, G of M times d sigma. And that is exactly the area of the image G of M, right? So corollary, another corollary here, if you have R a subset of the surface M, where R is oriented, if the Gauss map is 1-to-1, either K is either positive or negative, anyway there's no sign change, alright, then the total curvature of the region is just plus or minus the area of the Gauss map image of that region, where the sign matches K. And we already saw that actually we saw that in play for the torus when we looked at the total curvature of the torus. That was happening, so like K positive, K negative. So the Gauss map inside the torus maps to the whole sphere. The Gauss map of the outside of the torus actually maps to the whole sphere, because the torus is basically the image of two pi angle segments. So you have like 2 pi and 2 pi for both of the angles for the torus. But to cover the sphere, you just need like pi across a 2 pi. And so if I have a pi worth of one angle and 2 pi worth of another angle, I can cover a whole sphere, and I can do that twice with the torus. And one, of course, the positive and negative total curvature of those different pieces cancel out to give us 0 total curvature for the torus. And then I think O'Neill has another example about a catenoid. A certain subset of the catenoid maps onto the whole sphere, modulo the north and south poles. Anyway, I'll let you read that in O'Neill. But anyway. Alright, so I'm going to cut it off right here. I have a little bit more, and I'm just going to pick that up again because I'm not sure what on earth this is all about.